Okay, so following up from the previous lecture, last week we were discussing igneous rocks. This week we are discussing sedimentary rocks. And sedimentary rocks are essentially formed in two different ways. One of the primary ways is bits and pieces of other rock material that are mashed up and mushed up together and loosely held by some type of cementatious material or some kind of binding agent. And that is our typical sedimentary rock. Another one would be our what's called an evaporite. Um, of some type. So it's more of a something that comes or precipitates out of solution uh, when we have a high brine type of environment and we have um, uh, rocks or minerals that precipitate out of solution and form into a rock, essentially, or our sedimentary rock. So for the more physical uh, chunky sedimentary rock where we have bits and pieces of older rock material. The other rock material is um, crushed up by terms of weathering, and we come over to chemical weathering, which is the chemical breakdown of that rock by solution, and this is through oxidation and hydrolysis. So if we have for example, a fresh piece of granite that is exhumed from the earth through tectonic forces or whatnot, um, the surface of that granite will start reacting, albeit very slowly, with whatever atmosphere. So through the introduction of oxygen molecules along the surface of the granite, water that trickles on that will coat the granite during rain showers. Um, there's going to be a very slow chemical process that will gradually break down the surface of that granite rock and ultimately change its form and weaken its state to where the individual grains of the feldspar, the quartz, and micas, those will start to fall out of place from that granite. And those individual grains will kind of clump up together somewhere down the line, have some type of binding agent, and we will end up with what we traditionally know as a sedimentary rock. So, for example, we have that rock, and then we have this yellow layer, which is generally what's called a rind of that rock. So it's similar to an orange rind, so the orange peel of it. We see that outside layer, it's still granite. However, there's a definite chemical change that has occurred to that rock, and this is from uh, everything as I just mentioned, from the oxidation, hydrolysis, uh, even the UV light from the sun's rays will speed up the chemical breakdown of that rock. One way to tell whether we're looking at a weathered surface of rock is to simply take a rock hammer, as we see here, and to break that rock into smaller pieces. And once you break through that rind layer, you could see that layer of weathering, and you see the fresh exposed rock underneath. So that brings us into physical weathering, and this is the physical process of breaking down that rock. So this is from frost, salt crystal growth, pressure relief fracturing, landslides, um, earthquake, earthquakes loosening up rocks from cliffs and having those rocks tumble down and smash into smaller pieces. So this is the physical breakdown of big rocks into smaller rocks. Right. Although this is not a rock, but this will also give us a sense of physical weathering or physical breakdown of the surface. And this, of course, is a road that has been deteriorated to the point where it needs to be repaired. But we see that this is from uh, having a lot of vehicles travel along this road, and that weight and pressure eventually has destroyed this road. So in classifying sedimentary rocks, we have clastic and crystalline. So clastic is where we have the broken pieces of rock that is cemented together, and this is categorized by a definite grain size, a definite composition of those individual grains, and also the matrix, a definite type of sorting and roundness of these individual grains, versus crystalline, which is composed of pure crystal growth or pieces of organic materials. An example would be fossils or plant matter. So we see that on the figure on the left, we have a bunch of shells that are, or fossils of shells that are cemented together by a crystalline structure. So it's most likely a calcite type of growth that has cemented the fossil shells together, opposed to what we see on the right, where we have a lot of individual grains that are touching each other that are cemented by something else that is not a crystalline structure. And we see examples of the type of roundness and even the composition of the individual grains, where we see on one side we have shells, the other side we see rounded pebbles. We also want to pay attention to the different grain size, because grain size can give us indication on depositional environments as well as the amount of energy at which this particular sedimentary rock was deposited. So going from left to right, we see very fine grain particles. We are unable to see any particular grains on these two flat pieces of sedimentary rock. And then if we move towards the middle, on the side in the shadowy part of this rock, we can see that it's slightly bumpy. So we can pick out individual grains, and it looks like it's slightly more coarse than the rock on the right, and versus the rock on the furthest right, where we are able to pick out individual pebbles out of here. So what does this tell us? It tells us a lot about the depositional environment, where in a high energy flow state, we are able to move larger rocks. So we will find larger pebbles in a high energy flow state versus something that has a very small grain. This would be a low energy area. So you want to think about this in terms of a very fast moving river. We would be able to move these large pebbles that we see on the right. And once that river loses that amount of force and energy, those pebbles will settle out, and they will, over time, form into the rock that we see on the right. However, further downstream, where there is still enough energy to carry individual grains of sand, we start achieving the depositional environment of the middle rock. And then much further downstream, or even in a even lower energy state, such as a dune or a desert, where we have a lot of wind-blown sand, we could end up in environments where we're creating the rocks that we see on the furthest left. So in texture, we want to pay attention to the individual grain size and the grain shape. So is the grain rounded? Is it jagged? Right. So in here, we see that the grain is jagged. So what does jagged mean? Jagged means that the individual grains haven't traveled far enough to where the tumbling process and bashing into each other of these individual grains, that energy usually will will grind away at the sharp edges. So as a rock moves further away from its source, the more rounded it will get. So in a very high energy area where the material does not move very far, so for example a landslide, we would typically have more jagged type of rock. So the individual grains in here are very jagged, so it gives us indication that these individual grains broke off from some type of parent rock that was fairly close by, and it did not travel that far because a lot of the sharp edges are still preserved in this a piece of sedimentary rock. And then the opposite of that, we see a lot of round grains here. And the round grains tell us that this particular rock, or at least the individual grains in here, has moved a considerable distance away from its source rock, its parent rock, because a lot of these sharp and jagged edges have eventually ground down and worn out. So we're left with these very smooth spherical type of rock that make up the individual grains of the sedimentary rock. And finally, we want to pay attention to the arrangement of the individual grains for the texture. So are we looking at big rocks on top of small rocks, a big mix of everything? Are the rocks all the same size, or are they different sizes? Right. Versus this image compared to the previous image. This image here, we see a lot of the grains are very similar in size versus the previous image, where a lot of the individual grains are different sizes. Okay. So in this chart that we have here, on the left side, we see grain size, and we see grain size from pebbles all the way down to clay. So it gives us classification in terms of the millimeter size of what we should call the individual grains, from pebbles, granules, coarse sand, medium sand, fine sand, silt, and clay. So clay is the smallest particle. It's very smooth. It's very silky. Silt is still a little bit gritty, and then we increase the grit level as we move up in size. Right. So this is the classification of size. And if we go to the top right side, where we have rounding, we have angular, subrounded, and well-rounded. And this is the shape of individual grains. So are the grains incredibly jagged and sharp, which means that they did not move that far from its source material, so that would make it angular, or it tumbled incredibly far away and it's now very rounded, so it would be a well-rounded grain. And then somewhere in the middle we have a subrounded. Now know that this is the real world, so we'll have something, we'll have a spectrum of angular all the way to perfectly spherical. So expect to find stuff several levels in between, and we'll just have to use our best judgment in terms of classifying what the roundness of individual grains are in our sedimentary rock samples. So in the center figure of the right column, we see sorting. So sorting is essentially the distribution of the different sizes of our grains. So we have poorly sorted versus well sorted. So poorly sorted means that we have a distribution of a lot of large grains and small grains mixed together, versus well sorted, a lot of the grains are the same size. And then finally, at the bottom right, we have grains in matrix. And this is referring to the individual grains and then the matrix, so the binding stuff or the stuff around it. And we want to give when working with the hand sample, we want to eyeball a rough statistics in terms of what is the dominant grain. So we want to pick out the dominant grain, and we want to observe what the matrix is, the stuff in between. And the stuff in between could be a very kind of a fine sand, or even a cementitious material, or even a clay-like material. But if the dominant grain is a very large pebble, then that's the dominant grain that we're looking at, and that's what we use to categorize in terms of sorting, rounding, and grain size. In determining the sedimentary rock composition, this is referring to what the individual grains of that rock are made out of. So is the individual grains made out of quartz? Is it made out of feldspar? Is it made out of amphibolite? And this gives us indication in terms of figuring out whether we're looking at something that is clastic versus something that's chemical. So in a clastic form of a sedimentary rock, we are looking at a rock that is made out of essentially other rock material. So a type of potentially igneous, metamorphic, or even another sedimentary rock that has been worn down, broken, and now is a individual grain within this current sedimentary rock, versus looking at something that is chemical. And this is organic material, shells, plant matter, and so forth. And this also includes chemical residues and crystals of minerals that have precipitated out of solution, such as calcite or even halite. When looking at graded bedding, all that means is we're looking at a very distinctive pattern in the cross section of this sedimentary rock. And this could be at various scales. In a very large scale, we could look at this in terms of meters. In a very small scale, we could be looking at this in the centimeter scale. So the size of this can vary vastly. And this is all dependent on the type of flow or how big of a flow we're having. So all gradient uh, is the pattern of having a lot of progressively smaller grains going from a very coarse or large grain rock material to a very fine grain material, and then the repeated pattern of that. Generally, we are interested in that because it gives us indication of the type of current flow that that would have happened during the depositional period, as well as a repeated pattern of this current flow. So for example, in a hurricane-prone area or a flooding-prone area, geologists would look at the sedimentary structure to look at this repeated pattern to perhaps predict when or forecast when we would expect the next flooding event or next major hurricane event. So in real life, we can expect to see some graded bedding, such as what's shown here. We have a little card that is in the image for scale. So another type of bedding is cross bedding, and this is the individual layers of sand that is blown and eroded in a very beautiful pattern that creates these fan-like shapes. And in real life, what this looks like is pretty similar to what we have here, where we see the diagonal lines of the sandstone that are opposite direction of some of the layers below it. This is what's called cross bedding. And in depositional environment, we discussed this a little bit earlier. This is where we can use our individual textures, so the grain size, the sorting, the roundness, the percentage of grain to matrix material, and we can kind of go backwards in time and estimate where this sedimentary rock came from, or even where this type of sediment came from. So if we're looking at a lot of jagged type of material, we can expect this to be very close to the source rock. And when I say jagged type of material, I'm referring to the individual grain sizes. So if the individual grain sizes is very jagged and pointy and sharp, and it's in this sedimentary structure, then we can expect this rock to not have moved that far from the source. So we would look towards the mountains or anywhere where we would expect a parent rock or a source rock to break off and not move that far. So perhaps somewhere in the glacier side or the alluvium fan side is where I would expect to have more jagged grains for rock. However, if we go closer to the beaches, for example, in the deltas or the streams, we would start to have a lot more finer grained material, more rounded, and going into the beach, we'd have very fine grained, very well sorted material. So everything has been tumbled nice and round. A lot of the large rock material that was heavy was left behind or broken and pummeled into smaller pieces at which the low energy current of the stream can carry towards the beach area. And then if we progress further into the ocean, this is where we start having our clay and silt-like material that would collect in the deep marine area, and that would eventually turn into a very smooth, fine-grained sedimentary rock in which we can't see or notice any type of grain in there. So it'd just be a sedimentary rock of just almost cementitious material. So the main points to remember in a depositional environment is that it's all about the amount of energy that environment has. So in a high energy state, we are closer to the source. Grains are going to be very poorly sorted and they're not really rounded at all. And we would expect to see a assortment of large grain, small grain, fairly jagged material. So think of a tall mountain where the landslide material is very sharp and pointy versus a low energy environment such as a beach or delta where we're very far from the source rock material and the grain that we're able to pick up with our hands is much smaller, typically a lot more rounded, and they're a lot more uniform in terms of size as well.